Yuan, maybe you could go ahead and share your.
Yeah, let me share. You see my screen okay, right?
Yep.
Let me, how to play a view. Let's see, view full display.
Control L. Control L.
Yeah. Full screen.
Option L, you see here. Here.
Two more down.
Two more down.
More down.
Oh,
There.
yeah. Sorry, full screen. It's really, my eyesight doesn't also work well. Anyway, so you see the screen, okay, right? Let's how to get rid of
Maybe
this.
not. I'm not sure that you see the bottom. Maybe.
Already?
I can see the full slide. I think that's fine.
Okay,
Okay.
that will disappear. Let's see.
Okay, I think we should probably go ahead and get started. I think we're okay. So, yes, good morning, good afternoon, good evening, depending where you're calling in from. Welcome to the last day of the full ACPC workshop. This is day 2 of our Deep Convective Cloud section. And today we're using a little bit different format to try to stimulate more discussion. So we're going to start off the morning or start off the session with a number of lightning talks, quote, poster talks, where you'll get a quick introduction to to each one of the topics, and then we'll break out for about 50 minutes or so to go into breakout rooms and have some more detailed discussions on each of the topics. After a short break, we'll come back towards the end of the session for some discussion about modeling activities and next step forward for ACPC. So we're going to start off with these 3-minute talks. For the speakers, we're just going to let you go and jump in at 3 minutes if you're still going strong to try to move us along to give us time for discussion. So without taking any further time, our first speaker is going to be Danny Rosenfeld. So Danny, please go ahead.
Yeah, I will present the contrasting effects of fine aerosols and sea salt coarse aerosols on both shallow or warm clouds and deep convective clouds. Each of the topics was presented separately by Zhenxin Pan and by Fan Liu on the deep and shallow clouds, respectively. Next slide, please. Joanne, can you move the next slide? Anybody hear me?
Yes, I hear you. It's like slides. You didn't see?
No.
Anyone else? Did you
We're
see
still-
like
The
slides?
slide is not advancing for me.
No, it seems freezing.
On my side, it is. Maybe.
Also, your picture is frozen.
Oh, okay.
I can do it from my side.
Danny, I think we need to do them all together. Just
Okay, but if Joanne
somebody
can.
else have them.
So
Let me
each one,
share.
I
Let me
have,
share again. Let's see what
I
happens.
think each one may also have a copy.
That's the last one. Okay, that's good. Okay, so on the top we see the effect of combined effect of coarse sea salt and on the x-axis and the fine aerosols with the lines that was presented by Fan Liu. That I just want to remind us that the fine aerosols are increasing the effective radius, are decreasing the effective radius this way. fine aerosols for the same coarse aerosol decreasing the effective radius, but they are increasing the coarse sea salt is increasing the effective radius, and respectively increasing the rain frequency and the rain flux. And if we see what is the effect on deep convective clouds on the cloud top temperature, we can see that when you have more coarse sea salt, the cloud top temperature is decreasing, and it is decreasing more. And you see that when you have more fine aerosols, it is increasing. So here you see the opposite two effects on that. The coarse sea salt increasing the lifetime of the precipitation of the deep clouds, because mainly, and that happens mainly when you have a large amount of fine aerosols with the red line, because that's when the coarse sea salt can restore most of the warm rain. And sorry, that is the lifetime, yes, and the same applies for the warm rain. And we see how the lightning is decreasing with more coarse sea salt. But when you add, when you go from a few fine aerosols in the blue line to more fine aerosols in the red line, the lightning, normal lightning, that is the lightning yield, how many flashes occur for 1 cubic kilometer of rain is increasing. So next, last slide, please.
Anywhere at 3 minutes. So if you can.
Okay, so that's a message. This is the mechanism which most of you already could grasp anyway. Thank you.
Let me try full screen again to see if it works. Maybe it's because. Okay.
Okay, our next speaker is going to be Yue Zhang. Please go ahead.
Hello, everyone. I'm going to talk about the impact of wildfire aerosols and also the new particle formation on the Amazon convective clouds in dry season. So our objective is to investigate how wildfire will influence the convective clouds through releasing abundant aerosol particles and also through the new particle formation. And as we know, like for new particle formation effect here is mainly about the ultrafine aerosol particle effect. We conducted a model simulation at 500-meter resolution using WRF coupled with spectral beam for a local convective case over the Amazon on September 30 in 2014. So we did a sensitivity test on the 4 aerosol scenarios. And for the aerosol settings, we obtained the sets from the WRF-CAM simulation with advanced aerosol nucleation mechanism for SOA production from the wildfires. As we see here for the wildfire simulation, we include all the wildfires, and for background, we exclude the wildfires. And for the blue lines are about the wildfire without the new particle formation. And we also further test about the new particle formation. The major contributions from the local region or the PBL region. And as we find that the aerosol, the wildfire aerosols increase the intensity of surface rain rate and also the frequency from the moderate to large rain rates. And also this actually is mainly because of the UAP effect. And for the clouds, cloud top and cloud thickness here, we see that the wildfire aerosols reduce the warm and also the modest mixed phase clouds. This will lead to this leads to a strong radiative cooling during this stage, but this is mainly because the cloud albedo effect. And at the later deep convective cloud stage, they are increased and as well as the envelopes. So this will lead to radiative warming. And as we notice that this radiative warming is also mainly from the UAP effect. So but UAP effect does not impact the warm rain and mixed phase, warm clouds and mixed phase clouds much. So we also do not see the cloud or the radiative cooling as much. So which means this effect is mainly because of the large aerosols.
Anyway, you're at 3 minutes. If you can wrap
okay,
up.
and I think I will stop here. If you are interested in this study, we can discuss more in the breakout room.
Okay, great. Thank you. Next up is Ross Herbert.
Hi there. So this is work done with Philip Steer at the University of Oxford. And in a similar vein, we're looking at wildfire impact to the atmosphere over the Amazon. And so we're trying to build on what is probably quite a small number of studies that have looked at the kind of widespread remote observations over the area. And so we're using an 18-year climatology, which has spatial and temporally co-located instruments. So we're using MODIS, Ceres, and AIRS. So we have clouds, radiation, moisture. So we can really look at lots of different aspects from different instruments, along with precipitation meteorology. And importantly, we're also using Terra and Aqua satellite overpasses. So we have a morning overpass and afternoon overpass to try and contrast, look at the diurnal response in the observations. So in the results, in this panel A, this is just showing that there are these diurnal responses. So this is liquid water path as a function of AOD. This is 1 degree gridded data set. So all this 18 years of data from September. So in the morning, so the top plot is basically showing as you increase the aerosol depth in your scene, you increase the liquid water path. So this could be seen as maybe rain suppression or aerosol cloud interactions. Whereas in the afternoon, so the lower plot, you can see initially this increase in liquid water path followed by this kind of consistent decrease. And I'm going to concentrate on this next because it's quite an interesting thing. And so in this plot B here, it's basically showing that this increase and decrease is consistent with an increase in convection and a decrease in convection. So these are just 3 different things I'm looking at. Percentage domain where the liquid water path is over 400 grams per meter squared. So just showing convective grids. Basically, you see this increase up to AOD of 0.4 and then a decrease, and you see that in the precipitation as well. So it's really nicely showing this invigoration of convection, which might be what UA was showing previously, and then this decrease afterwards. So the change in the convection has massive implications for the cloud field. In plot C below there, let's look at the frequency distribution of cloud fraction of liquid, total, and non-liquid. So the blue colors are for low AOD, and the red is for high AOD. And you can see this quite strong shift. If you look at the total cloud fraction, this strong shift from these lower cloud fractions to higher cloud fractions. And so this has been driven by this kind of large regime changes due to the convection. And in the summary, we've also looked at Ceres, and it basically, it shows, we see this consistent cooling effect due to these rapid adjustments of the cloud field. And it's consistent in the morning, in the afternoon. We can subset it for local meteorology, large scale meteorology. We always see the same stuff. And so it suggests there's quite a lot of cooling happening in this area. So come and talk to me and I'll discuss it more with you.
Great. Thank you very much, Ross. Next up is Mariko Uwe.
I'm Mariko Uwe of Stony Brook University. Can you hear me?
Yes, we can hear you, please.
Okay, I will present the analysis of impact of aerosols of convective properties using cloud resolving model simulations with different environment, polluted case and clean case, coupled with the radar simulator and cell tracking algorithm and radar observations. And first, we will evaluate the simulations using long-term next-rad observation dataset. As you can see, example is the middle panels. This is the relationships between ecotop height and the maximum build vertically integrated liquid, and color represents the frequencies. We used here the 4 years next-rad observation around the Houston area. So as you can see, this showed some nice storm evolution. As you can see, the maximum build at the lower altitude and going toward the higher altitude. We created the same plot from simulation dataset using using radar simulator and cell tracking algorithm. One findings is that the simulations well represent vertically integrated liquid and ecotop height. However, the simulation shows maximum reflectivity at lower altitude compared to the observation. We also compared the polluted case and the clean case. Compared to the clean case, the polluted case showed fewer cells and more frequent short-lived cells. And also polluted case showed stronger maximum updraft. The example is figure on the left side. This is showing the maximum updraft as a function of normalized cell lifetime, normalized lifetime. A color represents the difference between polluted case and clean case normalized frequency. Line represents the median value of the maximum updraft at each beam. As you can see, the polluted case showed a slightly stronger maximum updraft in the early stage of the cloud lifetime. The polluted case also showed deeper convection. The example is the right figures. This is showing the ecotop height and the maximum build. The color represents the difference between polluted case and clean case. This plot shows the larger build when ecotop height greater than 8 kilometers and higher ecotop height when for the lower builds below 10 dB. I'd like to highlight that this study provides the unique approach to evaluate the simulation using long-term radar data. And also this study will suggest the need for high spatial temporal resolution observations to analyze the cell evolution to see the aerosol impact. Yeah, that's all.
Great, thank you, Mariko. Next up is Steve Salibi.
Thanks, Mike. So in this work, we're looking at aerosol impacts on hydrometeors and microphysical processes in ordinary convection. And the simulations that we're looking at here come from the ACPC model intercomparison project. So in looking at the aerosol effects, each of the team members on this ACPC MIP team simulated a day of kind of ordinary convection over the Houston area with 8 different ACPC MIP models. And then for each of these models, we did individual cell tracking from the TOBAC cell tracking algorithm that Sean Freeman spoke about yesterday. And then after we identified the cells, then we did our analysis specifically on the cell cores, and we could come up with these cell composites that were specifically isolated on the area of convection rather than doing this type of analysis from a domain-wide perspective. So just one example is shown here. So in the lower left panel, there's the figure that says cell tracks lasting 20 to 60 minutes. So from one of the models, the different little lines on there of different colors, those show the identified cells, cell tracks. And so they're scattered throughout the domain. They're of different length of duration, different path length, but we're able to track those and then isolate our analysis just on those cells. And so the 6 panels up toward the right there are just an example of a couple of fields that we've looked at. So the panel in the upper left of that 6th panel that says rain, this is an example time height plot of total rain mixing ratio within the cell composites. And this is a normalized time. So the beginning of that scale at 0.0 is the beginning of the time that the cell is identified. And then the very end of that is when the cell is no longer identified. And we've tracked on mid-level vertical velocity. So for the rain, you can see that bullseye in bright colors there at around 3 to 4 kilometers. So we've identified that the rain maximum is about 3 to 4 kilometers. We can see it picks up after the cell starts to grow, and then it kind of diminishes toward the end. And then we can look at the aerosol effect on rain there and the delta rain panel kind of in the upper middle. And the bright blue there just shows a suppression of rain due to pollution aerosols. So we see a reduction in the collision coalescence process growth for rain. And then we also have, for many of these models, we have these process rates that we can look at to try to understand why we see this change in different hydrometeor types. So for the delta evaporation rate, we can see the blues there at the bottom indicate a reduction in evaporation, and that's going to come from largely the reduction in the rain due to pollution aerosols. The bright reds there come from an increase in cloud water. So we have this reduced transition from cloud to rain in the polluted scenario. And then the bottom three panels show the ice. And the ice is a little more sporadic in how it's distributed. So the ice time series there show the ice forms a little bit later in the life cycle of the storm. And the delta ice there showing the change due to pollution aerosols is a little less consistent. It varies over time and height. We can kind of correlate the delta ice there with the delta freezing rate. And we see some correlations between the process rate and what we see in the change in the ice field. So in the poster session time, I'm going to show all the MIP models, and we'll see that the liquid phase response to aerosols is pretty similar among all the MIP models, but the ice phase is quite a bit different. And so we'll focus on some of those similarities and differences in the poster session.
Okay, great. Thank you, Steve. Okay, so I'm up next on, just want to give you a quick update on the extended tracer field campaign and a review of some of the first light data. So you've heard a lot about tracer already, but hopefully you know that it was originally motivated and conceived by a series of ACPC pilot studies, some of which you've just heard about. So I'm the PI, at least for the Department of Energy part of tracer, but this really represents contributions from a large community of researchers, including many folks on this meeting today. So the campaign is currently underway. We've been out there since the beginning of October. And the main part, or the long-term part of the campaign goes all the way through the end of September. But right now we're preparing for the intensive observation period that's going to begin. The main site at LaPorte, Texas is pictured in the upper right-hand corner there. At this site, at this point now, we've collected more than 7 months of data. And I could say, happily say that most of the instruments are running quite well with little downtime. We've got some really great data sets. We've also got some of the first implementations of the radar cell tracking. So this is a really unique component of the campaign where we're going to be using software-driven automated cell tracking to look at the evolution of the deep convective cells, to look for some of these signatures in the microphysics that might be due to aerosols. All the data that we've collected so far is publicly available. So if you're interested in looking at that, there's the website. If you have trouble with that, please let me know. And I'll emphasize that the modeling activities, which again, mostly are motivated by the ACPC work, are being organized by Ji-Wen and Sue, and we'll be talking about that a little bit later. To add a little bit more, so during the intensive observational period, we're bringing a lot more instrumentation into the area, both fixed and mobile sites. We also are adding increased radio sounds to capture the thermodynamic environment as it evolves through the afternoon hours when convective growth is going on, and this radar cell tracking. And a very cool thing about tracer is after we kind of set the seed for things, it really grew. One of the main additional components led by NSF is the ESCAPE project, which is adding airborne, mobile, and other platforms, and also doing some ACPC relevant modeling activities. Lastly, I'll point out some of the data on the right-hand side, just to give you an idea of what we have already. So the top plot there is from the vertically pointing cloud radar, gives you an idea of the vertical profile of cloud fraction, in this case for a month, but we could produce this over the entire seven months. One thing we've noted so far is lots of shallow cumulus cases, not so much isolated deep convection, but we expect a lot more of that during the intensive observation period. And on the bottom there is a plot from the single mobility particle spectrometer, which gives us aerosol size distributions as a function of time. In this case, this is from October to January, and shows really the variability in those size distributions with contributions from local sources and also transported sources. So if you want to talk more about the tracer campaign, please join me in the poster session. And with that, I'll move along. I have a second slide, but please skip past that one, Ji-Wen. Okay, and so our next speaker is Jinhua Yin. Please go ahead.
Can you hear me?
Yes, we can hear you.
Okay. Hello, everyone. Today I wanted to introduce our four-track algorithm for convective thunderstorm system. We call it FACS, from ignition to complete dissipation. I'm Jinhua from Wuhan University, Danny and Phil's group. Track the complete life cycle of deep convective system is very important for exploring its role in the climate change. But in previous work, they usually track the system largely following the largest core. Meanwhile, the servers detrained from the core also were ignored. This will affect the calculation of DCS radiative forcing. In our FACS method, we continue to track the split and merge cloud. At the same time, the detrained servers from core or NV still be tracked until it dissipated completely. Finally, all convective cloud is combined as one complete system. Here, we show one tracked case. In this case, we can say our FACS method can track the system from the newborn and merge another core and split servers and final dissipated. And a final from the statistic result during the 2012 in tropical area, we tracked about 12,000 DCC cases. And we classify them based on the lifetime in 6 hours interval. The panel A shows the average and the total rainfall amount. We found even the short-lived system have less average rainfall, but because it's a very large number, so the total rainfall amount is close to the longer-lived system. And about servers, after the core dissipated, we found it can continue live up to 10 hours. And it still accounts about 16% of the total area of system. And this is very necessary for calculating the DCC radiative forcing. That's all, thank you.
Okay, thank you. Next presentation is by Chongfeng Zhao.
Hi, Mike. Okay. Hi, everyone. So today I would like to talk the distinct impacts on the precipitation start and peak time by the aerosol over the East China. So actually, this is done by my student, Sun Yue and I at the Beijing Normal University. So in this study, we use 5 years data in summer for convective clouds and also some stratiform clouds. We divide them into these 2 types, but here I only show the results for all clouds. 3 study regions have been selected. One is NCP, is the North China Plain. The second one is YID, is the Yangtze River Delta region, and the other one is the Pearl River Delta region. Based on these 3 regions, we can see the difference of aerosol impacts on the precipitation time. So we use the study data for include the hourly PM 2.5, the precipitation hourly data, and also use the GPM precipitation type, which include the convective precipitation and the stratiform precipitation. We also use the ERE5 methodology to derive the low tropospheric stability, the wind shear, and also the relative humidity. Try to know how this methodology affects the interaction between aerosol and the precipitation. So we first define the precipitation events, which is the continuous time, the hours, for the precipitation. That means there's no precipitation for 1 hour before and after this event. So based on the events, we can define the precipitation start time and also the peak time. So we also use the 4-hour average PM2.5 to represent the aerosol amount, because use that we can know the aerosol relative effect that need time accumulate. The bottom is the result. The left one is the statistical results. The first row is for the start time. The second row is for the peak time, and the left one is the start as the ACP. The middle one is YID, and the last one is PRD. From that, we can see the different impacts on the precipitation time by the aerosols. For example, for ACP, the precipitation start time is advanced about 3 hours by the aerosols. And also the peak time is also advanced. However, if we see the PRD region, both the precipitation time and the peak time has been delayed by 2 hours. And also for the YID, there is almost no change for the precipitation time. Then why? We think this is associated with the precipitation time, the aerosol type, which is the aerosol relative effect plays the dominant role. So the right one is two regions. One, the up one is the I think the relative heating rate, the profile. The bottom one is the vertical velocity. From that, we can see for the ACP, the absorbing aerosol is dominant with the heating effect. And for the PRD, the scattering aerosol is dominant with the cooling effect. So based on that, the convective, I mean the LTF, the low top stability becomes more unstable for ACP region, and for PRD region it becomes more stable. That makes the precipitation time advanced over ACP region and it delayed over PRD region. We also do the sensitivity analysis for the meteorology and found the relative humidity, the low tropical stability, and the wind shear all can affect the advance time and the delay time. I will stop here. Thank you.
Thank you. Thank you. Let's move on to Lin is up next.
Hi, my name I'm Lin. I'm from Texas A&M University, and our work introduced and improved convective cloud microphysics scheme for use in global climate models. Previously, the microphysical processes for convective clouds are usually neglected or oversimplified or even neglected, hampering our ability to study the response of convective clouds to aerosols. And previous studies already developed just a handful of convective cloud microphysics schemes. However, the representation of the cloud microphysical process rates in those schemes are mostly adopted from the stratiform cloud microphysics scheme, which fails to reflect the characteristics and features of convective cloud. So the objective here is to improve the convective cloud microphysics scheme for use in global climate models. So in the lower left, I show you that we improved one convective microphysics scheme by first characterizing the cloud ice and snow particle terminal velocity using the more physically based terminal velocity schemes, and by detraining snow to form stratiform emerald cloud, and by adding a grapple category with a set of grapple microphysics, and by constraining warm rain initiation and generation in convective cloud. On the right, I show you the impact of our scheme on the clouds and precipitation simulation. And overall, most of the climate metrics are improved consistently. For example, the cloud radiative forcing, our scheme reduced the two negative bias of cloud shortwave radiative forcing over both the tropics and latitudes when the warming formation process is constrained by observation. Moreover, our scheme also increased the frequency of occurrence of heavy precipitation, which agrees better in the trim with the trim estimate. And most of this increase comes from the convective clouds. So now the common bias of more light precipitation but less heavy precipitation is alleviated to some extent. Moreover, our scheme reduced the overestimation of the convective ice water content over, say, India and Amazon and several other convective active regions consistently over tropics and latitudes. And I look forward to seeing you and talking to you more in detail later. Thank you.
Okay, great. Thank you. We're going to move on to Mika Vaught.
Hi, I'm Mika Vogt, and I, along with Drs. Isabel McCoy and Robert Wood, am presenting this poster, Absorbing Aerosol Choices Influence Precipitation Changes Across Future Scenarios. For this research, we evaluated 4 shared socioeconomic pathways, or SSPs, from SIMIP6 scenario MIP simulations. These represent different possible policy decisions over the next century, along with 2100 forcing levels. As can be seen in the time series of global mean absorbing aerosol optical depth shown here, these 4 scenarios have different absorbing aerosol trends with SSPs 1-2.6, 2-4.5, and 5-8.5, all exhibiting aerosol cleanup, while SSP 3-7.0 has little change globally. Previous research has shown that precipitation changes are strongly affected by changes in long-wave emission and short-wave absorption, which are impacted by changes in temperature, moisture, well-mixed greenhouse gases, and absorbing aerosols. In this research, we used the atmospheric energy budget to understand and quantify how the different aerosol changes between SSPs affect global and regional precipitation changes. And we found changes in atmospheric shortwave absorption to be well fitted to changes in water vapor path and absorbing aerosol. And using this fit that we developed along with global atmospheric energy budget specified by equation 2, we were able to quantify the absorbing aerosol contribution to the hydrologic sensitivity. This is represented by the bar chart shown here, where we focus on SSP2 and SSP3 due to differences in absorbing aerosol changes. SSP2 has a higher apparent hydrologic sensitivity than SSP3, with absorbing aerosol being the largest contributor to this difference. In our poster, we also present a similar analysis we conducted for regions with striking changes in absorbing aerosol over the 21st century, where we again find absorbing aerosols to be first-order contributors to the atmospheric energy budget. And we also approximate the impact of absorbing aerosols on precipitation using 2 other methods, 1 as a residual in the fast precipitation response, and 2 in a multiple linear regression for precipitation changes to changes in absorbing aerosols and temperature directly. These, along with the atmospheric energy budget analysis, are found to be in relatively good agreement for each SSP. And we conclude from our analysis that aerosol changes associated with policy choices have a large impact on the atmospheric energy budget and thus global and regional precipitation change in the 21st century. And thank you all for your time, and we invite you to join us in our breakout room to continue this discussion.
Great, thank you, Mika. Next up is Chen Chen.
Hi, this is Chen Chen, and this work was done by 5 excellent undergraduate students. They are Shaohan Wei, Ronghu, Gudongze Li, Xiaobing Tang, and Wei Wenhui Xu. Now they study in 5 different universities and institutes as graduate students. So we simulate a squall line occurred during April 23rd to 24th, 2007 over Guangdong province, China, using Wolf model and the Thomson scale in order to investigate the impacts and scavenging of aerosol particles by hydrometers, the aerosol regeneration due to complete evaporation of liquid drops, and the effect of dynamic transport on the number concentration of aerosols. So we studied 2 types of aerosols, including the hygroscopic particles and non-hygroscopic particles. And the results showed that there was a negative correlation between the precipitation and aerosol concentration near surface. Here in the left figure, the black control lines denote the precipitation area. During the development of convection, we can see the reduction of aerosol concentration near surface in the precipitation area for both hygroscopic and non-hygroscopic particles, while the heavy pollution area appeared around the non-precipitation area near the gas front due to the dynamic transport. So at the lower panel, at the upper troposphere, we found the number concentration of hygroscopic particles was reduced, while that of non-hygroscopic particles were increasing. So by comparing the impacts and scavenging rates by different types of hydrometers and the nucleation scavenging rates, it's showing that the droplets and nucleation contribute most to the aerosol scavenging, followed by the impacts and scavenging by the raindrops at the lower troposphere and the snow at the upper troposphere. And the droplet nucleation and the ice crystal nucleations were the dominant scavenging processes for hygroscopic and non-hygroscopic particles respectively. And we found that the variation of aerosol number concentration was the result of combined effects of cloud dynamic transport, the wet scavenging, and the regeneration process due to the evaporation of liquid drops. And the regeneration process mainly occurred from the surface to the 10 kilometers altitude. Thank you, that's it.
Okay, thank you very much. And our final presentation is by Jin Zhang.
Okay, thank you, Michael. And I'm gonna give a brief introduction of how the lightning and convection will affect the ozone and NOx in the upper troposphere. So we have combined 3 different kinds of data sets, like the ozone sound chemistry model and the high resolution satellite observations. Firstly, for the ozone sound, we conducted campaign in the last 2 years, and we finally got 2 different kinds of convention. And in detail, we released the ozone sound before the convention, and another one just during or just after the convention. So by comparing the profiles at the different times, we can see that both the ozone and water vapor mixing ratios are higher after the convection. And then we assimilate the profiles and the lighting data into our chemistry model. And we find that the chemistry contribution is about 5 to 10 times than the dynamic contribution. And especially the lighting loss can reduce the chemistry contribution about 40%. And we also investigate different chemistry reactions, and I don't show them here. And finally, we use the detailed high-resolution models and outputs into the retriever of the satellite. So we can clearly derive the lighting loss signals and even the production efficiencies as shown in the bottom figure. And recently, we focus on the lighting loss in the Arctic because many papers in the last 2 years, they show that there may be more lightnings in the future because of the climate change. And the Arctic is very special because for the polar orbiting satellite, there are many overpasses over the same site for several hours. So we can track the lighting NO2 using the TOBAC showing yesterday. So if you want to talk more about the effect of the lighting or the convection, we can jump into the poster session later. That's all. Thank you.
Okay, great. Thank you very much to Jin and all the presenters. We're running just a couple minutes behind, which is pretty nice. So now we're going to move into the breakout sessions, and we have about 45 minutes for those breakout sessions. So we encourage you to try to attend at least 2, but maybe more than that, and we'll try to give you a heads up about halfway through to switch breakout rooms. Andrew or anyone else, is there any other details we need to? There we go. Now the breakout rooms are set up.
Yep, I don't think so. So 45 minutes, you said, basically. So we'll do a warning after 23 minutes for switching.
Sounds good.
Okay.
Is
Is Xinjiang not having a breakout room?
The recording has stopped.
Oh, I think you're muted. Sorry, I can't hear you.
Did I miss one?
Yeah, I was hoping to join Xinjiang's session, but I don't see it.
It's at the bottom.
Oh, there it is. Okay, thank you.
Mark, we can actually close all rooms. There's a button there if
We have 9 minutes till the next session starts. So maybe we don't even need to kill the rooms yet.
okay.
But soon we should, so that people at least have a chance to.
It says, I think Angie
there we
did
go.
something.
There
Yeah,
we
all
go.
black
Okay.
room will close in 20 seconds something.
Sounds good.
Yeah.
So then we'll take a short break and start in, it looks like about 8 minutes or so.
Yeah.
So Jim, we have a 10 minutes break.
Yes, we could take a 10-minute break now. And then we'll come back and start with some of our discussion, modeling discussions.
Oh, sorry, Michael. I guess I could have left things going during the break, but at least this enforces a break for everybody.
This is a good, I think people could use
People
a break.
need coffee.
Yeah.
Especially those of us on the western side of
Yeah.
the most western part of the day line.
Okay, great. See you a little bit later.
So we'll reconvene in 10 minutes.
Hi, Sue.
Hey, June. How you doing?
Good. How about you?
Nice early morning again.
I actually had a stomachache those 2 days because disruption of like I wake up early 5:30. I really love me because I'm not early person.
I'm not an early morning person either. And then you have to get showered and all the rest. Whatever. Yeah, whatever. So it's coming right.
Anyway.
Yeah.
Okay.
Hi, Andrew. How you doing? Yeah.
Good. Also getting up early.
Yeah.
Although I rode my bike to work actually at the crack of dawn. There was nobody on the road. It was really pleasant. Students are all gone from Boulder. It was really nice.
Yeah.
Benefits of getting up early.
It's a little damp this morning here along the Front Range. I don't know how it's down your way, but we've had
We're getting a lot of clouds.
Mm.
Did it rain up there?
We had rain last night here, which totally
Oh man, you're
surprised me.
lucky.
Yeah.
We didn't get any rain.
And they didn't forecast it, so I was like, we'll take it.
Now
We got to talk to them about that. I mean,
now I learned the benefits of being in the Middle East as far as time zones.
Yeah.
yeah, exactly. You're in the. If we're gonna do this, you're in the middle.
You're right in the middle, Danny. Yep, absolutely.
Right. Middle East, as it's.
Yeah, well, there you go. It's halfway between East and West.
Spot on.
It's a good thing you're not in Hawaii. That's all I can say.
Oh my word! Yes, for sure.
Well, Pacific Coast is pretty bad, so I don't like these mountain time people complaining.
I'm not complaining, Andy.
We're just offering comments.
And by the way, what is rain?
What is rain?
Yeah, exactly. Don't ask Danny; he doesn't know.
I forgot already.
I'll take a quick picture and send it to
you. You know what? You want to know about rain? Ask Philip.
Yeah, now you're talking. Now you're talking.
Very dry.
Now you see why I'm researching rain. I'm overcompensating for childhood deprivations.
Okay. Okay. Glad to have some laughter before the session. Last session. Okay, I think we can get started. And yeah, this is the last session of the workshop, and we're going to have a lot of discussions. And the first discussion is about tracer modeling plan. Well, also related to what ACPC, what we are going to do. Let me share the screen. I'm sharing the screen right now, right? You see my screen?
Yeah, we see it fine, June, but you might just put it into presenter mode. Yep.
Yes. So soon we prepared some slides, just trying to stimulate the discussion. So during field campaign, during the tracer and the escape field campaign, this is the modeling work that Zach label will be needed. And here is everything is preliminary, and he's looking for feedback. I'm not sure Zach is here or not. But anyway, this is the forecast runs, but the purpose is to assist with forecasting, but also provide an ensemble of model simulations for analysis of aerosol cloud precipitation interactions. So those are the different model configuration proposed for the ensemble. For example, aerosol probably have just 2 scenarios. For microphysics, there's 3 random proposed: Morrison, Thompson, aerosol well with P3. And then PBL, there's these 2 considered like non-local and include local effect. I mean, one of them, I don't remember exactly. I think YSU considered the non-local effect as well. So as ACPC, this is the initial boundary condition. There's a few options we can try. So
can we discuss this now, or you finish
Yeah,
first?
I think I was going to say, Julian, I think we should discuss this now, right? Because Zach has made this available to the whole team, right? He's managed to secure an extensive suite of computational cores, and he is open to ideas. He's seeking inputs as to what people would like to see. These model runs will be available, as far as I understand, to everybody on the team. He's looking for people to assist with the analysis. And Juan and Mike, do correct me, because we had a meeting with him if I'm speaking incorrectly about what he's offered. But I mean, I think he will be running on all days following our latest discussion, even on days that are not convectively active, because those are also clearly useful to everybody. And I think he's looking, from what I understand, for people to really make good use of these and analyze these. So I think it's worth discussing now. Danny, I agree.
Yeah, so for example, here are low and high aerosol concentrations. I suggest to add also sea spray aerosols. You have parties over ocean, and as appropriate, we can add with or without, because we saw, based on the presentations that I just made, and the two other full presentations by Van Loo and Zenshin, that they are very impactful, and we cannot possibly ignore it.
Yeah, it's a good point, Danny. Other points from anybody? And Zach he sent out a request for input. So I think we must, Juan, maybe we must send that even further afield, actually, and bring in all of this ACPC team into those requests, because I think that only went to the tracer team, right? Is that correct?
Yes. So I think it's even Zach probably not in the modeling group team. I send only to the modeling group group. So I send one for the link to seek for the input on the variables, the lead and the frequency. So that is the Google spreadsheet. I can maybe make it available to the entire ACPC.
We would need to check with Zach, but my impression is he's looking for inputs on what to add to this, as well as what to produce, the kinds of variables that people are looking for. He's looking for
so that is the main information in the Google spreadsheet. We have that the variables you like, the output variables, and also the time frequency. That is the input he's looking for. As for the model configuration, last time in our model modeling group meeting, we had some discussions about the domain setup, the resolution, and other things. So on that side, I'm not sure definitely he's welcome input. But there's no particular document for that
Yeah, you're right, Jen. I'm not sure he's looking for changes in the model setup, but he's certainly looking to hear what people want to see produced, frequency of output and so on. He's also, from what we understand, going to be keeping history restarts, portions way through, should people want to have access to that. He could rerun on some scenarios, or people could take it and rerun simulations themselves for research purposes and so on. So I think this is actually an extraordinary data suite of simulations that this team could draw on. I think it's a very exciting opportunity, actually. So
yes, yeah.
So G1, just one minor thing. So Zach is funded through Escape. So this is going to focus on the first 4 to 6 weeks. So that's one detail to keep in mind here. And we did indeed, his message went out to the entire tracer list, which includes lots of people in ACPC, but maybe missing a few folks. So if you didn't get that and want to give some input, I think rather than send it out to the whole list, you could contact me or Sue or Ji Wen, and we can make sure you get that that information.
Yeah, both excellent points, Mike. Thank you.
Yeah.
By the way, P3 is your scheme, Sue?
The P3? No, that's Morrison. That's Hugh and Jason.
Mariband, Jason Mariband.
Yeah.
And we used it a lot. Huh?
I would love to see the bin emulating scheme.
It's in Wolf for a while. We used it, in our MC3 field the CRM in the comparison. We used a lot also recently for our climate model. That's one of the major tasks I'm needed to modify it to put in the our Easter SM in DOE. It's advanced.
You're talking about the bin scheme, right, Danny? That's what you.
No, bin scheme is too heavy,
expensive.
For that.
Yeah.
But you're emulating bin scheme.
Yeah.
That's what I was looking for, because I think that is getting as close to bin without actually having to spend so much.
You're talking about the RAM spin emulating? Yeah, that would be really nice, Danny, but it's Zach's running, he's running it in the WARF scenario. So I think
so you don't have.
Yeah, we're not implemented in WARF, but I think what we can do ultimately, and Steve and I have been talking about this, is picking up some of these cases post field campaign and then rerunning and comparing. So I think that would be useful. Yes, I agree.
So also one point to mention that last time in discussion, basically I mentioned that we want to modify the schemes to make they connect with the Aerosol or have a simplified Aerosol budget, because otherwise usually those are just a fixed drop-in number concentration. You change the Aerosol concentration, which is just the low and the high, and it's a fixed number, which is not the way I would use for the aerosol card interaction. So that is something we changed those, at least the Morrison scheme and P3. We have such aerosol, simplified like a 2-moment aerosol, which have some assumption on the source, but we do have the droplet activation to remove the aerosol, and then the precipitation, remove aerosol. You have this simple budget to change aerosol mass number. It's not like a full chemistry. I know a full chemistry we cannot afford, but add a simple budget for prognostic aerosol. That is the way which I would suggest to for aerosol impact.
Yeah, I see no disconnect between the measured aerosols in tracer and the input aerosols here.
Yeah, right. Because this is a forecast run, probably, I don't know. Here, probably.
Yeah, that's a problem, Danny, and I don't see any way around it right now. I think Zach's intention is to pick what we consider, or what he considers as a clean scenario and as a polluted scenario, because as Juan says, these are forecast simulations, right? So we do not have a way to bring that into the simulations. So that is certainly more challenging as we move. And I think, Juan, maybe we should move, because some people are asking about, what's coming next. These are, so that's, I think we must be clear, that's Zach's NSF escape contributions. And now these are the different options for tracer that Juan's going to present here. So
So yes, so for this is mainly from actually also in the ACPC deep convection roadmap we put in there before. So post-field campaign, we have a few options. The first one here is that is the one basically following on what Sue did on the ACPC model in the comparison project. And this one, but for this time, we do have much well-observed cases to evaluate. My suggestion is that we want to do something probably a little bit differently also in the modeling side. For example, for Houston case, we probably cannot avoid just ignore the oven heat effect. So we my study showed that it's a significant impact on the sea breeze circulation. So this is something I would like to encourage people include the over canopy model, and also for aerosols, for the ACPC modeling comparison project right now, we only have this one mode, which is also pretty large aerosols. So we want to maybe have multi-mode. We have like a ultra-fine mode, a fine mode, and maybe a coarse mode. This is something I would think will be more realistic to realistically simulate the convection over Houston. The second option, which is the following on what we did for the MC3E field campaign, there's a CRM intercomparison study. In there, we use just WRF, similar to what Zach did, but we perturb 8 different macrophysics schemes, as you can see here. So we use different macrophysics schemes. We didn't try PBL yet, but we do here. We can also try different PBL schemes. Those can give us here. I also think we would like to have 2 golden cases with contrasting thermodynamic and dynamic features. This is something this is just an example showing, we do like from our ACPC MIP study, you can see a very large spread. Here for vertical velocity, even just for macrophysics, we see very large spread in the vertical velocity from different macrophysics schemes, and much larger compared to the observed one, which is this gray. And then, but we will be able to, if we just turn off the ice macrophysics, we can see the model spread is much reduced. And this is the mean of this with 4 macrophysics. You can see overall model converged, and also the vertical velocity agree with the observations much better compared to the mean value for the 4 macrophysics. So this just show example how this can help us identify the major processes responsible for some of the biases. And this one of them can be a study proposed to WMO cloud modeling workshop. They always look for cases to for this workshop, and there's another option here. We're going to discuss basically what the community, ACPC community interest next. So here's the third option I want to mention before we go into the discussion. So this is some particularly from global model perspective, like Yin and Paul Ulrich. We actually are interested in the also global model intercomparison with the regional refined mesh. Some people call the variable resolution, for example, in the MPass. So this is, you can zoom in on this location. This is 3 kilometer RM. The outside domain is 1 degree or 50 kilometer. It depends on you. You can set up the different resolution. But this will allow us to basically how the global circulation, local or regional interactions, two-way interactions considered well to address the problems and that Guy presented on that. My kid. Anyway, this is some modeling activities which I shared a spreadsheet to collect information from the tracer modeling group to coordinate the model simulation effort, and also to this is also help observational people to try to understand what kind of simulations are going on, and if they have particular simulations they're looking for to collaborate, they can reach out. So our discussion, data analysis needed, this I probably want to skip because probably we will not have much time to discuss. Let's go to the discussion item. So the things I just mentioned, the options, I just mentioned that basically we would like to have your input on what efforts do we feel that ACPC should focus on and who will be interested in participating. That is something we want to initiate the discussion. We can continue on later in the tracer modeling group. If you didn't join the group yet, I encourage you to do so if you are interested.
So June, how about we turn off this, stop sharing so we can all bring up faces and let's have a discussion on this. And I think, yeah, that's better when we can all see one another. I think there's several things, as you say, June, several things to consider here, right? We have 2 efforts on the go. One is the ASR tracer modeling activities, and the other is the ACPC modeling activities. And we need to decide whether these should be the same activity. A lot of the people are overlapping. The initial ACPC modeling activities led in a fairly large part to the tracer proposal and what was going on there. In my own opinion, it seems to make sense to combine efforts. I'm not sure it makes sense to run 2 separate parallel efforts. I think we should all, consider being on board. We all focused on tracer anyway, and decide what we as ACP and tracer want to do in moving forward. So I think it probably makes sense, at least in my own opinion, to join those efforts and move forward on that. Okay, and it seems like everybody, at least whose cameras I can see, and if your camera's not working, you want to express opinion, please put it in the chat as well. But I think that's what the team is saying, is that we should all move forward. So then the trick becomes which of those 3 options, because Juan presented 3 options, which of those 3 options makes sense for all of us to be involved in? Because I think we gained a lot out of the first ACPC MIP, and this is like the fruit of our works coming out after the field campaign for the second. So I think that's what we want to hear from you guys, is which of those options seems to make sense, right, from that perspective. So thoughts, floor is open. Okay, well, that was easy, Juan. Yeah, go for it, Steve.
So my thought after seeing all of this is that in having looked at, all the MIP models and kind of having discussion with the different participants is probably the option 2, I think, that Jiwin showed, is see if we can identify 1, maybe 2 cases. And since a lot of these folks are contributing, their own time to run these simulations, maybe we could find just 1 or 2, limit the amount of effort from all the other teams, and then see if we can pick 1 or 2 really great cases that overlap with tracer and escape, that we can kind of do the same intercomparison again. And now, but with some good observations from Tracer to help us decide which microphysical processes we're getting correctly and which ones need some additional work. So what can we get the most bang for our bucks, sort of?
So in essence, Steve, what you're saying there is take what we did before from the MIP and repeat that, but now we have this extensive suite of observations with which to evaluate. Is that correct? Is that your thing?
Right? But be very, very, very picky about which case or two that we choose. Something that everyone can get on board with, so that we don't, have too much of a time and effort demand on those that aren't directly involved in Tracer.
Yeah, Philip, your thoughts?
Yeah, I broadly agree with that thought. I think it's important. I mean, Steve's talk showed how terrible things look in a way. The models look very, very different. And obviously the whole Tracer idea is to constrain some of this, to really focus the efforts on getting some constraints. And I think we, as much as I like to add more complexity as well and more realism, but we have to be careful that we separate the uncertainty in the differences due to aerosols with the cloud microphysics. So something where the aerosols are quite consistent across models and then looking at the response is, I think, still valuable. There might be additional work where you have more realistic aerosols and maybe time varying aerosols, but once you do that, you have no idea why the models differ in the response. So I think we need a bit of both, probably.
Yes, that's a good point, Philip. I do want to raise a question that Sonia put into the chat. She was stating, just as an FYI, quite a lot of this bunch are not funded in terms of participation in Tracer and or ESCAPE. And Sonia, you're absolutely correct. That's been true of ACPC for a long time. And in fact, the original MIP study, it was really conducted on fumes. Most of us just kind of try to pull it out of scenarios wherever we could, sort of carve out a little bit of time to work on that. So that's, I think, has always been the sort of mantra of ACPC, is to come together as a group and, bring whatever energy and efforts we can, but there was never a sort of structured funded basis behind it. So from that perspective, from the ACPC perspective, we hope that people can contribute in ways that they can, but fully recognize, there are certainly constraints in that regard. So Sonia, does that answer your question, or do you want to talk more to that? Okay.
Yeah,
you get a thumbs up.
I would like to add here that the rewards to this effort has been so far the occurrence of Tracer. And now when we do this work, we need to start to think in our mind where it should lead to in practical terms that will reward us further in scientific terms and probably also in proposal opportunities.
Yes, Danny. So talk more to that in terms of what I agree conceptually, absolutely. Expand a little more on that. An example.
We'll get some insights about several processes that are critical, and then since they were not in the focus probably of the measurements in Tracer, for example, just hypothetical, could be or could be not the role of enhanced supersaturation, which will be revealed in the model in secondary activation in the latent heat release. That is not being measured now in Tracer, but could be a major focus of a future campaign.
So your view, and I think it's a great view, is models, hypothesis leads into field campaign observations, learn new roles, models again into another field campaign. That's what, right, yeah. And I think that's, ACPC, I think, is demonstrating, its effectiveness in helping steer the next campaigns coming down the line. So I agree. So yeah, absolutely. Other thoughts?
Could also prompt satellite missions of new kind.
Correct.
Yeah, we will have a discussion on that in the next session. We'll discuss Tracer ACPC direction. So here we do have, relevant to Danny's point about the data needed. So for this time, I think for model evaluation, we really want to develop, which the slide I skipped, now I want to mention it. So the integrated data sets in the like aerosol meteorology condition, radar observations, and they have this on the grid scale, which modelers can easily use, and how this integrated data sets developed from the observation of people. This is really important, and particularly related to the tracked, cells. We have this RHR operation for radar track with the radar tracking now from observations. That would be very, very, excellent. I would say the data sets never happened before. We can actually compare with the model, the tracked cells. I would like to really have observational people on board, so we can do much better this time. Yeah.
Yeah, that's a good point, Ewan. I mean, that's the whole new development in and around Tracer, both, tracked from the observations and the models, which I think we'll learn an a whole lot more than we did in the original MIP studies. So if I summarize this, because I think, Mike, the next item on the agenda is supposed to be happening now, Ewan, but maybe what you're telling Ewan and me from this point of view, it's a combined ACPC Tracer approach that we want to repeat the MIP post field campaign with 1 or 2 golden cases and really bring in the observational assessments while all the time keeping in mind where the next opportunities go. Is that an accurate summary of what we feel about this? Okay, awesome.
Yeah, I think so. Also, I would think it will be easier for more people getting involved, because if we use the fixed model, for example, Wolf,
yes.
like Sue, maybe you will like this.
Yeah. I'll wave goodbye.
So anyway, I think, that's a more reasonable way probably to move forward for ACPC on Tracer. Yeah.
So then I guess the one remaining thing is how many people, and we don't need to discuss this now, but I think Ewan and I would really encourage, and taking into account Sonia's considerations, we fully understand that, but we would really encourage as many people to get involved in this post the campaign. We will send out the details, the model setups, as we did for the previous MIP. And we were thrilled. We had 8 different models involved in the previous MIP, all again, just working on fumes of funding, literally sort of squeezing by. Hopefully we can encourage again a lot of community involvement. And, the more models, the merrier is really kind of how we view that. So.
Yes, Sue, I'll add that if this is really, and I think this all makes a lot of sense. This is how ACPC should do things. We need to focus on a specific thing. But I think we can use that even to help drive DOE and where their funding is going to go in the next cycle, and maybe to help Sonia and other people bring some funding in to help expand the participation. So I think this is good, and we should get it in front of our management quickly.
That's an excellent point, Mike, actually, because Sonia, to your point again, there's only a few modelers funded now as we're going into the field campaign for specific modeling activities in the field campaign. I think, and Mike, please correct me, the intention always has been of ASR to fund post-campaign modeling activities, correct? I think that's what you're saying, right? So yeah.
Absolutely. And this could help define the direction, I think.
To drive that. Yes, thanks, Mike. It's an excellent point.
Maybe next workshop, we can invite the RMS program managers to attend.
Yeah, that sounds like a good plan. We'll need to get our ducks in a row. Let's first select our case studies and things, but yes, absolutely. Okay, Mike, I think we've run more than our time, so I'll step off and hand over to you.
Yeah. I mean, one last point I'll make on this is we should definitely have an observational, get the modeling component is super important, but have a strong observational component to this too. And I'll work to help organize that part of things.
Right. Yeah.
And Mike, don't forget the course aerosol composition. It seems I want to make sure that it is covered. Given the importance of the sea spray that has been emerging.
Yes, you can ask Sue. I've been talking to her about that already, and as part of the reason we had Maria give her presentation yesterday. Okay, great. So do we want to move on, Ji-Wen, then? So this first part of the discussion is really focused on the kind of shorter term and some of these things we're thinking about. And now I think we want to open it up a little bit more than that even. And Ji-Wen, you made a slide to give a few of our thoughts on
yes,
kind of some of the next things we're thinking about.
Yeah, we have the list for a few things to stimulate discussion about this is really about the ACPC direction, and also some interesting and outstanding issues raised in past 2 days based on the presentations. So, you know, because this is a group really about aerosol cloud interactions. On aerosol side, we want to move on. I mean, particularly related to this community, we worked a lot on the aerosol concentration change, how that would impact clouds. But I think we probably should move forward on the aerosol size distribution. You know, we see ultrafine particle impact because in deep convection, we have high super saturation in very clean conditions. This could activate those very small particles. Then 5 aerosols, which usually we call accumulation mode, and then coarse mode. This is coarse mode a lot related to sea spray aerosols, sea salt, but the sea spray aerosols also has small ones. And those marine organics, they also can be good at iron. So this is related to the second point, which is about aerosol composition. Because the composition determines if the radiative effect is it's strong or not, or if they can serve as CCN or iron. And giant CCN basically has also very different effect, as Daniel also mentioned. So those things we want to consider probably in our studies in the future, focus more on those aspects. And then for the, let me dismiss. Yeah, on convection class, we see talks, particularly from Guy, we want to emphasize the interactions at a different scale or teleconnections. For example, subtropics and tropical teleconnections. Also, we see ice multiplication, which can be changed also because of the aerosol. And ice multiplication, which is we call the secondary ice production, in convective clouds, maybe in many other type of clouds as well, there's no good understanding, and we do have some recent measurements for that to improve. So that is something on the iron part, because primary ice circulation, we usually don't consider, in a lot of models, the ice part is not considered, the ice formation is not considered to connect with aerosol yet. So that is the part I would encourage. For example, we use, for my study, where we use DeMalt to connect with dust and Mokransky. to connect with marine sea spread aerosols for IMP. Another aspect can be focused on the airborne radiation, because airborne clouds has a strong radiative impact for the legs. Another thing is the joint effect with other factors. For example, our trace zone, we do have a big urban area there, so urbanization maybe need to be considered. They have a strong joint effect with the aerosol, aspergenic aerosol. Also, climate warming, like today we see a talk from Miguel. So that's it. That's the topics, just trying to bring up for discussions. And your input is really welcome. Let me add.
I have a question. Philip and Sue, you had this plan of doing global cloud resolving simulations with aerosols. Could it be aligned with the tracer field campaign and then compare the regional simulations with the global simulations and the observations?
Possibly. I mean, we haven't discussed this here in great detail yet, but possibly, but I think it is a bit remote because we want to be really idealized, and exactly to address the point that I mentioned before, to separate the concerns of uncertainty in aerosols, which we just prescribe super simple, from the response of the microphysics. But I think many of the same models will hopefully contribute to both. And I think you're right, it should be linked. It's I'm just not entirely sure if it's explicitly sort of the experiments need to be linked.
But you actually mentioned, raised a good point in the involvement of global CRM simulations, the role in this community. Basically, because the direction is moved to, in climate model, we are moved toward a global cloud resolving, global convection permitting. So that's why in the earlier discussion, I showed this RM3 kilometer, which is one of the ways to cheaper ways, like just zoom in a region, but have a global context to look at that is the way based on my opinion, a little bit more flexible way before we get to the global cloud resolving model, because it's really expensive, right, in the computational costing. So that is I think there's many groups already work on that. There's a quite big study, but they may not focus on aerosol impact. So it's a good opportunity for us to initiate such works to focus on aerosol impact.
I think oh, sorry, Danny, go ahead.
Yeah, I would look at it from another angle. Once we identify cloud resolving models that are capturing the variability due to aerosol in a relatively well, we have a way to see how well or what do we lose when we go to simulating the same domain, but with GCM parameterization. What are the global models capturing it well, or exaggerating or underestimating the effects? That will be a good way to propagate our results to the global scale.
I think these are all really good comments, right? And I think that's the sort of long-term perspective of where we need to go. But I think we also shouldn't lose sight of what ACPC is really good at, going after processes on the scales, on the convective scales for now. I mean, that's what this group is really good at. So I think there's a lot to resolve, both on the microphysics and on the aerosol representations at these fine scales, with a view to going upscale, be it GCMs or be it into global CRMs. So
I agree.
Yeah.
But given, I suppose, the guy, that he would either do that or do something else.
Yes.
We might as well attract him to do that.
Yes.
I think Lauren has a hand up. Lauren.
Yeah, hi. Sorry, so I'm new to the group, so I don't know if this is not in the purview of what this group is interested in, but I noticed there are very few talks on the Arctic, and if we're talking about incorporating global models in this kind of research, I mean, Arctic clouds are really poorly understood and can't be modeled well, is my understanding. So I thought maybe that would, if you're trying to move towards a global understanding, I thought maybe that could be an idea of something to focus on, but maybe this isn't the right group for that. I don't know. I just thought I'd just kind of test the water for that idea.
Yeah. Arctic probably for the low cloud group. The Arctic mixed phase clouds are generally dominate. For this is a deep cloud group, focus more on the deep convective clouds. So that's why probably we don't have talks on that.
Yeah, ACPC is focusing on several issues. We don't attempt to cover everything, but we try to make impact on very specific hot issues and in practical way. So we cannot spread too thin. Maybe in the future, ACPC will start working on the Arctic clouds, but presently we are too busy with what we have already.
Okay, all right, thanks.
And Lauren, most of us are not on the ACPC side of things. As Sonia raised again earlier, most of us are not funded specifically for ACPC activities. So we need to draw from, other avenues that support that. So we're living in the tracer mode just right now. But Danny's right. There's no reason in the future why other areas shouldn't be looked at. And it's great to have you on board and raising those questions. So awesome.
I'll share the screen again about those topics. Is the agreement that we want to for Aerosol, we want to move further on, consider different modes and also pay attention to composition.
It looks like Sonia has her hand up, so maybe she has comment on that. Or...
Yeah, sorry, I'm going to continue doing this way because I'm having internet issues. But it seems like a little consistent, Jiwan, under aerosols. I mean, shouldn't there also be a bullet about using more INP data in the future? I mean, we've been looking so detailed anymore at local CCN in our simulations, and yet we seem content to use global distributions of INP in all cases in our models that don't really fit anymore, or at least from what we know, there is a strong regional dependence there as well. So wouldn't we want to advocate for more INP studies as well?
Yes, Sonia, you raised a good point. One of the point here when I mentioned it, aerosol composition, which is really related, determine what kind of aerosol can be CCN, can be good ion. For example, dust and also marine sea spray aerosols, they can be ion, efficient ion. And that is also related to how the currently in the climate physics, a lot of this acid accretion mechanism, they are still just temperature dependent schemes. There are a lot connected with aerosol yet. So that is we usually need to change that to use the recent field campaigns. Recent model polarizations derived from field measurements. For example, Paul Demart's work generally based on the field measurements. They derived those parameterizations are easier to implement and can connect with aerosols. We do, yeah, well, there's a Europe, I think in European, there's a very good group. They organize the IMP data. Yeah, I can find that link and send to you if you're interested. Many past field campaigns about IM are connected on that website.
Yeah. Sorry, I just misunderstood your bullets here. So, all right. Yeah, I just want to make sure that—
it's not a misunderstanding. It's a good point to reinstate. Yeah.
Yeah, so and I could add on INP where, so during Tracer, we'll have, I think it's 3 fixed site measurements at the surface of INP. And then during Escape, we'll have the aircraft-based measurements also on this, I think on the spec Learjet. So yeah, I think that's something we don't always have in our convective studies, and we will have some constraints, observational constraints on that at least for Tracer.
Great.
Okay.
Philip has his real hand up, not his
Zoom. Sort of surprise people. No, just want to add support also to this anvil and radiation theme. I think that's what excites me quite a bit. We see in all the cloud resolving runs a lot of changes in the mass flux to the upper troposphere, radiative properties of anvils, and I think there's a lot to be done. It would be nice, so for the tracking that will present it on the deep convection, we have a product that also does the radiative properties, but at the moment we only do this for Severi. It would be quite nice to have a radiative property product from GOES for this, but that's maybe something to discuss offline.
Yes, definitely. That's actually, I have been looking for those kind of product. Thank you for mentioning it. Yeah.
And Mike, remind us, we have part of the Tracer team bringing focus on GOES to their field campaign. Is that correct? Or am I misremembering that?
Yeah, I mean, we have the team from Langley will be providing their cloud products that they generate regularly, and we'll be making requests for the high resolution GOES output. We won't always be first in list for those things, but we'll be requesting those.
Will one of the products be the shortwave and longwave aviation? Or 2 of the products?
So
yeah, that's a good. I don't know. I need to check on that.
You need to have such a product anyway.
Yeah.
Might be good idea to have a list what kind of properties they will retrieve with GOES. To list somewhere. I'm really interested in those GOES products because it's it's high resolution and it how very good also. I mean, in both spatial and temporal, the resolution very good. It's really good satellite product. I cannot see because I'm sharing the screen, Mac. I cannot see the chat and those hands up. Is there any other people? Let me stop the screen share. Okay.
I think Philip has mostly shared some of the information on the cloud product or the satellite products that he's been working with. So that's great. Thank you.
That is for Meteosat, doesn't cover the Tracer region.
Right.
No, that's what I mean.
Yeah, I'm sorry. I just don't have on the tip of my tongue what the products that the Langley Group produces. So so I could definitely get information on that.
I think I seem to remember though, Mike, some of the from their discussions with the, in our tracer meetings, I think some of these are going to be comparable. So I think they'll be really useful to this issue of the anvils. I remember we had a discussion on anvils during their presentations. So
yes, yeah.
I think the shortwave and longwave was some of their produced products, but as you say, we should check with them.
Yeah. Right. So I have a question for Ji-Wen and Sue, maybe just linking the discussion about kind of a tracer MIP to the first two items on here about the aerosols. So during the MIP, the treatment of aerosols is mostly on the number concentration and varying that between kind of clean and polluted conditions. Here we're mentioning more detail in the aerosols that would be included. Is this something we would want to do in this MIP, or do we want to keep it simple and stick with kind of the same format we used before? I'm not suggesting one way or the other, just asking.
Yeah, Mike, I think that's a good question. And when you look across the models, certainly in the first MIP, the representation of aerosols across those 8 different models is tremendously different. Steve can talk to this. He's just dug through each and every one of the models' aerosol representations. So from everything from initialization through to whether or not you advect aerosols, to the kinds of aerosols, to whether or not you keep track of it. So there's a tremendously wide range of aerosol representation. I think that if we are to be inclusive in the MIP and make sure that everybody can participate appropriately in the MIP, we're probably forced to go to using the most simplest representation, because in that way all models can participate appropriately. But I don't see any reason as to why, and I would see that perhaps some of this then gets captured in the actual follow-on tracer-funded studies, perhaps, as opposed to the ACPC MIP, or perhaps some people are feeling adventurous and want to now build some of this into this. I know, for example, for the original MIP, I'm certainly with Rams and with Philip's team, we did some changes. I know with Rams, we looked across the wide range of aerosol sizes. We tried out fine and coarse aerosol modes, and I think Philip, I think Max and Bethan might have done that as well. We looked at it. We haven't done the research associated with it, but I think that if people are interested, they can do that. But in terms of the baseline MIP, we probably need to keep it in the mode of what all models can look at just right now. That's just my opinion. Others may well have different views.
Yeah, thanks. I mean, that makes perfect sense to me. And depending on the different capabilities, people can do the next steps as PI projects or smaller projects. But for this kind of larger combined effort, it makes sense to keep it simple and as similar as possible to our first one.
Right.
But still, I think maybe we want to, we can use, constraint aerosol is indeed important. If we will have very wide range of setup, then you would expect we have a very large spread model results. So maybe, at least for typical mode observed from Houston, we can consider not just a single mode. That is, not that complicated to add, but it's a little bit more realistic.
Yeah, June, I'm not suggesting we don't do that. I think it's really important. I just think within the context of the MIP, it's hard for some models. We want to make it as easy as possible to have as many models participate in the MIP. But next steps for sure. I agree. These things need to be considered. Absolutely. So there's a progressive development, I think, is how we should view that.
One other way of doing it is to make a MIP in different tiers and say there's an absolute must, which is simple. And if there's multiple models that can do the more complex tiers, then that's great. And if not, then that doesn't work.
Yeah.
Yeah, I agree with Philip. I think that's a good way to go about it, because I'm quite concerned about being too restrictive on the realisticness of the aerosol formulation. Like if you eliminate a very fine mode, some Aiken mode or like a sub-Aiken mode, you basically eliminate the entire process of secondary activation, which might be really a key process. On the other hand, if you eliminate a coarse sea salt type mode, you basically also eliminate the entire set of processes that Danny's results that he presented here are referring to. So if you're too restrictive, you basically just become unrealistic. And so I think you somehow need to bring that degree of realism in that's required to capture the key processes.
Yeah, Andy, I totally agree. And I think in the first MIP, it actually operated in that way, but perhaps in a behind the scenes manner, as opposed to, we had all the models do the baseline. Then some of the models, I know Jiwan went on and looked at, the range, so did we, so did Philip, so did some other groups, but we could formalize that. Yeah, as you suggest, Philip, it's a good idea. Tier 1, tier 2, and so on. The trick is ensuring, people have time, energy, and resources to be involved, but those who are interested will, play the long game on that. So yeah, it's a great idea. Absolutely.
Yeah, a good compromise.
Indeed.
Yeah,
Indeed.
some people will not just for tier 1, but
yeah,
we can move.
Yep.
Yeah.
And some people's models are only designed to participate in tier 1. So let's get everybody on board there, and then progressively develop that. So.
One maybe related question is, how do we feel about aerosol radiation interactions? I don't think we discussed that yet. And in some areas, they could be quite important.
Yeah. So in Houston, we run the Wolfram simulations. We look at it, at least in our case study, I would say, aerosol radiation effect is not a dominant factor. So indirect effect is dominant. But in many regions, in the past, we did some work in China and India, and where black carbon, those absorbing aerosols, they actually have quite a bit of strong aerosol radiative impact. So if we focus on chaser, maybe we don't need to worry about that. At this moment, until we get very, very polluted condition.
So I might argue against that, actually, just to stir the pot a little, because when we ran the MIP, right, for the first MIP, we didn't allow aerosol radiation interactions to be on. We had to pick some simple compromises. Comes back to your point, Andy, about maybe overly constraining this. And we subsequently ran a suite of tests in terms of aerosol radiation interactions. And in particular, if we're talking about anvils, but also radiation reaching the surface and things. And we've done a number of sea breeze tests in this regard. And for example, if you don't include radiation aerosol interactions, you impact the sea breeze circulation quite extensively, because we know the sea breeze circulation is dependent on thermal gradients. And if you don't include that, you mess with those thermal gradients. And so we could end up changing all of that dynamics there in and around Houston from the sea breeze side of things. So it's something we need to talk about and decide on as a team. I just think the feedbacks to a number of the dynamical scenarios there could potentially be quite important. So we may need to do a few tests when we're setting up the MIP, the MIP design. But yeah, it's an important point, Philip. It's not something we can just say we're not going to do, right? We should do some tests, I feel.
It's even more complicated if you, in the MIP simulation, you want to add aerosol radiation interaction. It's actually much more complicated compare just add for aerosol, different aerosol modes or aerosol computation. Anyway, yeah, I think particularly if we consider black carbon, that's why I think our Houston generally we don't have this strong absorbing aerosols. That is something, yeah, it's definitely a component we want to talk about. But
and some of those models, as we said already have that included, black carbon. A lot of, I don't know, Steve, do you know offhand how many of the models have radiation aerosol interactions built into them? I think a good portion of the group participating do, but do you know that offhand?
I don't know.
Okay.
I mean, we have that in RAMs, but I'm not sure how many others have a complex interaction there.
Yeah, so a number do, but again, it could be built into this tier approach that we've been talking about. So, that could certainly be done, because given ACP's formulation and that we are not a funded body per se, we do have to be careful how much work we load on people in this regard. Hopefully the tracer funded scenarios can help with that, but I'm starting simple, including everyone, and then building up in these tiers, I think is a great approach.
Maybe it's a stupid idea, but maybe we can think of a way to do it like the MAC-SP, Max Planck simple plume model. So to have an aerosol radiative interaction, but in a non, like the aerosol are prescribed in terms of radiation. So you basically prescribe the AOD and single scattering albedo, and that's it, basically. So Ross have done it in a cloud resolving model. And yeah, maybe it's not too difficult to implement to other models as well. I think it should be not too complicated, I think.
And Guy, one thing we've done, because I've done some recent aerosol radiative interactive development with RAMs, and some of our simple tests, we introduced aerosol profiles with different types. So if we're looking at a sulfate type, it's going to be more scattering. And so we can kind of do some idealized test and see how much shortwave suppression we get due to various aerosol distributions and sizes and concentrations, kind of maybe spanning the range of what we'd see in the Houston area, and see how much attenuation of the shortwave we get to see if it's worth going down that path in full simulations. We can do it kind of an idealized 1D column and see if it's worth pursuing.
Yeah, that's actually a good idea, Steve. And then, then we could see, which of the tiers it should live in, right? If we see this huge effect, it's like, well, we better include it up front. Whereas if it's a lesser effect, then, we can maybe build it as something down the line, just as an idea. That's a good idea.
Another possibility is to use only one, in the high aerosol scenario, to simulate, to do only one run with the direct effects, but not do it for all the runs. And that way we will not increase the dimension by a whole number.
Yeah, Danny, absolutely. Then we can talk to, how much that talks to the variability. So, yeah.
Okay. Any other comments? I didn't see much observational people attended this time. Even Scott Collins was not attended. Mac.
How do you call me?
I was gonna say I'm looking at Danny, I'm looking at Mike, I'm looking at Andy, I'm seeing got a lot of observation people. Yeah.
No, I mean, sorry, I was more focused on the Jason Richmond on that side. I mean, Mark, of course, a representative of the, the observational people. But yeah, I think this integrated model observational data sets with aerosol meteorology and cloud precipitation, those combined together, those are the data sets that Scott Collins was very interested in developing for this. So I was thinking, that's from that.
I think that's a big focus for the observational side, both the kind of the Lagrangian view, so the cell tracking with the radars, and we saw a lot of the cell tracking with more operational products during this meeting, and then trying to relate that to the regional variability in the aerosol and thermodynamics, which we're going to have to kind of try some interesting techniques by constraining things with the measurements we do have there. But I think that's a big focus for a lot of the different observational components in Tracer, and we'll be doing everything we can to constrain each of those things.
So is Scott Collins leading on that, or or is that some person we can particularly ping on to?
Yeah, I don't know if there's for ACPC, I think I will probably be kind of helping to shepherd that effort along, but I think lots of different people are going to be contributing in different parts, and you've heard a number of those people talk yesterday and today. So yeah, I guess I'm the one on the hook to help organize those contributions.
Yeah,
it looks like Lauren has a question.
Yeah, I just since I just as an observationalist, I just thought, again, I'm new to this group, so but from my perspective, I think the secondary ice question is really important, and more observations would be really, really helpful, because from the observation perspective, you can't distinguish between, what's driving things, at least, well, I'm using remote sensing tools, but we see trends, but we don't know what's causing them. And the models can help, but I think having good observations for secondary ice production, to the extent that it's possible, would be really helpful.
Yeah. So for the tracer, we do probably, it's difficult to get those measurements for secondary, production right now.
I think in deep convection, it's going to be hard to isolate that part, right? We've done some work at BNL, and I'm not sure Ed Luke is still here, but doing this in polar mixed phase clouds, we've been able to isolate signals for secondary ice production. It's a little bit harder to do in deep convective clouds.
Well,
there was
I
a
think
paper.
That there is,
sorry.
I think that there is a lesson to be learned from ICE-T, where they tried to separate primary from secondary nuclei ice production, and they could not find ever any primary one.
There's a paper by Korolev and some modelers, and Fridland, I think. They looked in deep convective clouds, and I don't remember all the details, but I think that they felt more or less, well, that they believed they could say something about the secondary ice production in these clouds, and they believed it was important. I could share the paper. I don't remember all the details.
Yeah, I'm familiar with that. Yeah, this is mainly with tropic cumulus observations based on that. Alex Korolov, he had a review paper about it, and they indeed, particularly at the temperature between, I think, around -10, there's a very sharp increase in the ice number concentrations, which, it's not relevant to the primary IMP. They're pretty confident it's from the secondary ice production. But the models never can capture that, but because right now, most of the models we use hard-MOSEP parameterizations for that, but that is just one of the mechanisms for that, may not be the most effective one, particularly in the clean condition. The drop shattering and other mechanisms can be very important.
So I think I'm looking at the time and seeing we really have just a few minutes left in our time here. So I think maybe we need to wrap up, and I see Sue needed to leave. But I guess I want to say thank you for the great presentations in the deep convection section and the low cloud section earlier this week. And for these great discussions today. I think it's really helped define where we need to head in the short term and the longer term. Jiwen, I don't know if you have anything to add, and I think maybe we want to let Danny and Mingwei if they have anything to add at the end, but maybe Jiwen go first.
Well, just thank everyone. This is really a great workshop, and the participation is very great. Thank you.
Yeah, actually, the kind of discussion that took place now gave us some things to look forward and a feel of fulfillment for the great effort of ACPC. So I think that we should feel good about it, at least I do. And I'm looking forward to tomorrow morning, the morning in America, there will be the SSC meeting where we'll have a few new members that will be voted on. And also there will be a new co-chair. I feel that I have served it long enough that it's time to allow other people to serve this. Mingwei will continue longer to keep overlap and continuity. I'll stay in the SSC for another couple of years or so, at least. So I'm not going anywhere. I'll continue to be as active. And I hope very much that next year we'll be able to do it all in person. And if there will be a virtual component, will be in favor of those who cannot travel, but not because of COVID. So thank you, everyone. And I feel that we are just starting to take off. Thank you again. So the meeting is adjourned. Thank you. Bye.
I'll offer one more quick thank you to Andrew and the NCAR team for